All right, BTrees in just 2 minutes. A very quick introduction to what's a BTree. A BTree is not a binary tree or a binary search tree. Even though we will be talking about binary search tree as an underlying concept, let's talk about that first. So what's a binary search tree? As many of you already know, binary search tree is a tree where it's a binary kind of tree. So every node has up to two child nodes, and in that you store a value. The values are ordered by the search property. Binary search trees are generally self-adjusting, self-balancing trees. So that means you add a node to it, it'll automatically adjust itself, adjust the height of it, as you might have seen on the lecture on the binary search trees. So now, what is lacking in binary search trees? As we say, binary search trees are great magical data structures. So BSTs are awesome. They do everything in order, log, and time. So why do we really need BTrees at all? The two key motivations. In fact, what does B in the BTree stand for? That itself is subject to a little bit of a debate, because the author of the BTrees did not specify what B stands for, and we can probably have a whole another video on what B stands for. But let's talk about the two key motivations. Binary search trees are great, but they're great for when we are talking about within memory. Now, when you're starting to store things on the file system behaves differently from your random access memory. So in a binary search tree, if you have a tree of a height 25, that's not a problem. You're just simply going from one node to a child node to a child node. That's just like going 25 depth. That's perfectly fine. If you are storing those locations on the file system, you are going to do 25 lookups of the file system, which can actually become extremely slow. So that's a small problem. You don't want to do 25 lookups of the file system. So, and by the way, there are movements in the file system such as coming up with solid state drives, SSDs, which is another separate angle on how to improve it. But because you don't want to do the many lookups of the file system, what is one idea? You can simply increase the branching factor. So the broader the tree, the less will be the height, right? So that's a simple concept. The number of leaf nodes is b power h. If you increase b, the height will decrease. But the second key motivation is that the rearrangements in file system are very bad. When you want to rearrange, you want to adjust your self-adjusting binary search tree, perfectly fine in memory. But readjustments in the file system are really bad. So for that, you need flexibility and gaps, and that's basically what a BTree is. So BTree is a flexible data structure where a node has a variable number of child nodes. So it could vary between 2 and 4, or between 50 and 100, something like that. And that the 100 or 4 in this case is represented as the order of the BTree. And this variability allows us to have certain holes in the tree. So that means when we want to add a node, we can very easily add it. If we delete something, as long as it's within these bounds still, it's still okay. So you can have deletions without changing the structure. And as well as because you have a higher B value, a higher branching factor, the height will be smaller. And that is in a nutshell what a BTree is. If you want to read much more about it, feel free to follow the link to a bigger presentation about the BTrees, but that's basically what a BTree is. A BTree is a generalization of a binary search tree where you allow the node to have different number of child nodes. An example of a BTree is also a 2-3 tree, where it's a BTree where each node can have between 2 child nodes or 3 child nodes, and that allows us to already visualize the difference between a binary search tree. Okay, that's it. Have fun learning.